Have you ever stopped to think about the incredible secrets that are locked away inside our financial data? I mean, we're talking about trillions of transactions, information that could help us fight fraud, predict economic shocks, and maybe even build a fairer financial system for everyone. But there's this huge fundamental problem. All that data is intensely private. So how can we possibly learn from it without, spying on everyone?
Right, that is the central puzzle we're going to solve together in this explainer. We're going to look at a pretty brilliant new technique that lets researchers do something that sounds almost impossible: pull out these powerful, society-level insights from data while giving an ironclad guarantee that no single person's privacy is ever compromised.
So, first off, why is this so hard? I mean, for years, the standard approach was just to anonymize data. You'd take a data set, you'd strip out the names and the social security numbers, and you'd kind of call it a day. But it turns out that's like putting a padlock on a screen door. It just doesn't work.
And this is exactly where that old method completely falls apart. You start with what looks like safe, anonymous data. What a clever attacker can do what's called a linkage attack. They take your supposedly anonymous financial data and they combine it with another totally public data set. Think voter registration lists, which have names, ages, and zip codes. By matching up those common data points, boom, they can suddenly re-identify people and see their private transactions. So yeah, anonymization by itself is just not good enough.
This is where a much smarter and more modern approach comes into play. It's a field of math and computer science called differential privacy. And the important thing to know is that it's not just a guideline or a best practice. It is a formal, provable mathematical guarantee of privacy.
So here's the core idea behind differential privacy, or DP for short. You strategically add a small, carefully calculated amount of random noise to the data. It's done in such a precise mathematical way that the final result of any analysis is almost identical whether your specific data is in the dataset or not. And that makes it mathematically impossible for anyone to reverse engineer the results to find any single individual.
Okay, to really wrap your head around this, let's use a simple analogy. Imagine a census taker comes to your town and they have to ask a really sensitive question, like, have you ever committed a small crime? You probably don't want to answer that directly, right? So the census taker proposes this clever little system. Everyone secretly flips a coin. If it comes up heads, you have to tell the truth. But and here's the trick: if it comes up tails, you flip the coin a second time, and you just answer yes or no based on that second random flip. You never tell the census taker which method you used.
And here is the magic. The census taker still gets incredibly useful statistics for the whole town. They know the probability of the coin flips, so they can mathematically subtract that noise to get a really accurate overall picture. And yet, for any one person, your answer is completely protected by plausible deniability. No one can ever know for sure if you answered truthfully or if you were just following the coin. That is the genius of adding controlled mathematical noise.
Okay, so differential privacy protects the input data. That's part one. But how do we use those protected insights to actually create something useful? Well, the second piece of our puzzle is a really cool technique called agent-based modeling.
The easiest way to think about this is to imagine you're building a world inside a computer. It's kind of like you're playing a video game like The Sims. You create this virtual environment and you populate it with little individuals who all have their own rules and behaviors. Only in this case, instead of virtual people going about their day, researchers create virtual financial agents. You have your clients, you have your merchants, and you have your banks. And here is the absolute key: the rules these little agents follow, how often they spend money, how much they deposit. All of that is learned from the differentially private statistics that we gathered from the real world. So how do these two big ideas actually come together? This slide basically shows the workflow of the system the researchers built, which they call MoMTSimDP. First, they compute those private summary statistics from the real data, using differential privacy. Step 2, they set up the basic parameters for their virtual world. How many clients, how many merchants, that sort of thing. Third, the system teaches the virtual agents how to act based on those private rules we just learned. And finally, step 4, they just hit go on the simulation and it spits out a completely new, totally synthetic dataset that is both incredibly realistic and fundamentally provably private.
Now, all of this sounds fantastic in theory. It's very elegant. But the billion-dollar question is, does it actually work?
I mean, can a data set that was generated by a bunch of little virtual agents in a computer really be useful for serious real-world research?
Let's look at the evidence, because the researchers behind this, Azamuke and his colleagues, they put their synthetic data through a whole series of really rigorous tests to answer that exact question.
First, they locked down the privacy side of things. That epsilon value of 1.0, that is a very, very strict privacy budget. It means very little information leakage is allowed. And that delta setting, that means there is only a 1 in a million chance that the privacy guarantee could possibly fail. So in short, this isn't guesswork. It's a formal, mathematical fortress that they built around the original data.
And they didn't just create a tiny little sample data set either. They ran their simulation and generated nearly 34 million synthetic private transactions. That is a massive, useful data set that's on the scale of what a real-world mobile money system would see in an entire month.
And when they compared the patterns between the real data and their synthetic data, the results were pretty astounding. The original paper shows these graphs where the rhythm of the synthetic data, the daily and monthly ups and downs of deposits, withdrawals, transfers, it was an almost perfect mirror of the real, secret data. It ebbed and it flowed just like a real economy.
And finally, the hard quantitative proof. They used a standard statistical test to measure just how different the synthetic data was from the real thing. And the result was this total error score of just 2.0070. And for a test like this, lower is better. In the world of data science, a score that low is a fantastic result. It confirms the synthetic data has incredibly high fidelity. It's the real deal.
So, what does this all mean when you put it together? Well, it means we are entering a brand new era for research. This isn't just some academic exercise. It's a powerful new tool with absolutely massive implications for the future.
And as the authors themselves put it, this is a first. They're the first team to successfully combine multi-agent-based simulation, that's the MABS part, with differential privacy for financial data. They've essentially created the blueprint for how to do this kind of work safely and effectively.
So what does this actually mean for us, for you? It means researchers can finally dig into sensitive financial behavior without ever violating anyone's privacy. It means companies can develop much better tools for things like fraud detection. And maybe most importantly, it means valuable data sets that were once locked away in vaults can now be opened up for the public good, not just in finance, but in healthcare, social science, you name it.
And that really brings us full circle. We now have a working blueprint for solving this privacy paradox. It really leaves you with a huge question. What other profound discoveries, what other secrets are just waiting to be found if only we had a way to share all of our data completely safely?